In this video, we'll look at the graphs of exponential and logarithmic functions. First, we'll look at exponential functions, and then we'll look at their inverse, which are the logarithmic functions. So, a function is called exponential if it involves a base that's fixed and then a variable exponent. So the key is that the variable is in the exponent. So notice that's different from like x squared. In that case, there is an exponent, but the variable is not in the exponent. The variable is in the base. So this, when the exponent is a variable, that's exponential. This is not exponential. Even though it has an exponent, it's not a variable exponent. So looking at these examples, we're going to graph 2 to the x. 2 is fixed base and x variable exponent. 1/2 to the x. 1/2 is a fixed base, and then x is a variable exponent. All right, so let's look at these two. 2 to the x. First, I'm just going to make a chart of x's and y's, even though this is what we want to do always. So y in this case is f of x, which is 2 to the x. I want to review rules of exponents here. So if I have, let's pick, let's see, 2, 1, 0, -1, and -2 for our x's. Then I would have 2 squared, which would be 4, 2 to the 1, which is 2, 2 to the 0, remember anything that's a base that's not 0 raised to the 0 would be 1. 2 to the -1, that should be the reciprocal of 2 to the 1, so 1/2. And 2 to the -2 would be 1 over 2 squared, which would be 1/4. So we've got some points we can plot here. We've got 2, 4, 1, 2, 0, 1, -1/2, -2 1/4, and already it's hard to distinguish between these values. Whoa. But if we think about what would happen if we have a larger and larger x or a smaller and smaller x, let's think about that. When x is 3, we'd have 2 to the 3rd, which would be up to 8. When x is 4, we'd have 2 to the 16th, which is already off our graph. 2 to the 5th would be 32, and this is just going to grow exponentially, right? So as we move to the right, the graph's just going to get taller and taller very quickly. As we move to the left, we just have reciprocal of larger and larger denominators. So let's see, we'd have 1 over 2 to the, so we'd have a 1/4, somehow that disappeared from my graph. Then we'd have 1/8, 1/16, and these are just going to get smaller and smaller, but there's always a 1 in the numerator, right? So because there's always a 1 in the numerator, because it's always 1 over something, the values are never going to get to 0 for the function values. So that means there's not going to be an x-intercept. The y-intercept we can see is 0, 1. The domain, we should have -infinity to infinity. This graph extends left and right without bound. The range, though, we don't get negative numbers, and we also don't get 0, but we get closer and closer and closer to 0, so as an interval we'd write 0 not included, so parentheses, to infinity. And we graphed several points here, but what I want to focus on are these points where the graph has its most distinguishing curve, I guess. To the right, we have almost a vertical line, and to the left, we have almost a horizontal line. So it's right in this area that we see the shape the best. And the points that I'm going to call our key points are these 3, with x values 1, 0, and -1. So when I write points, what I mean are the key points that I want us to keep track of would be 1, 2, 0, 1, and negative 1, half. And really what it is I always want to use these x values to get my key points, because those are the x values that are going to give us that nice place where the curve is the most interesting. Not super steep and not nearly horizontal. So on this graph, 1/2 to the x, let's do the same thing. If x is 1, we'd have 1/2 to the 1, which would be a half. If x is 0, we'd have 1/2 to the 0, which would be 1. And if x is negative 1, we'd have 1 over a half, which would be 2, right? The reciprocal of a half. So again, what I'm doing for my points are taking the x values 1, 0, and negative 1. Let's plot those points. So 1, 1/2, 0, 1, and negative 1, 2. We could think if I have negative 2, I'd get the reciprocal of a half squared, which would be 4. And if I had x equals 2, I'd have 1/2 squared, which would be a fourth, right? So this one is going to go up as we move to the left and flatten out as we move to the right. But still, we're always going to have a 1 in the numerator, so we're not ever going to get to 0. And that means we're not going to have an x-intercept. The y-intercept is 0, 1, just like it was in the last one. The domain is the same as it was in the last one, negative infinity to infinity. And the range is also the same, right? We don't ever go below the x-axis, so we'd have 0 to infinity. So after those examples, I think we can kind of see some general patterns here. 2 to the x and 1/2 to the x had some common characteristics, right? Neither of them have an x-intercept. And that's going to be true for any base to the x, as long as the base is not 1. We'll talk about that in a little bit. So the base needs to be positive and not 1. But let's see, for the y-intercept, we always put x equals 0, and if x is 0, we'd have b to the 0, which would be 1. The domain, we can put any x up here and make sense of it. So the domain is going to be negative infinity to infinity, and the range will always be 0, and higher, 0 to infinity. And the key points, like I was saying, we want to use x equals 1, which in this case would give us b to the 1, which is b. X equals 0, and b to the 0 is always 1. And x equals negative 1. Anytime we have an exponent of negative 1, we have the reciprocal of b. Right? So if the base is a fraction, 1 over b ends up to be a whole number. So it's not that we always have a fraction when we have the x equals negative 1, but think of it as the reciprocal of the base. Right? So these are common characteristics of all the graphs that are a fixed base to the x. So let's look at a couple more. You can try these on your own and make sure you're getting it. I'm going to start with the points. So I always use x equals 1. 3 to the 1 would be 3. X equals 0. 3 to the 0 is 1. X equals negative 1. 3 to the negative 1 is a third. And I can plot those points. 1, 3, 0, 1, negative 1, a third. Now I can see from this that the graph is going to go up as I go to the right and level off as I go to the left. It's hard to get that to be looking like it's getting smaller but not crossing the x-axis. The y-intercept would be 0, 1. There would be no x-intercept. The domain is all real numbers, and the range would be everything above 0. All right. Then the next one, if I choose x equals 1, I'd have a third. X equals 0, I'd have 1/3 to the 0 would be 1. And if x is negative 1, I have the reciprocal of a third, which would be 3. So 1 1/3, 0 1, and negative 1 3. Notice this is just a reflection of the graph we just did across the y-axis. You'll talk about that when you get to college algebra or pre-calculus. If you take that course, we can talk about why that would be. But here's what our graph would look like. The y-intercept again is 0, 1. The x-intercept, none. And the domain, all reals, and the range, everything above 0. Right? There is what's called a horizontal asymptote, a line that's not crossed but is approached on the x-axis for these graphs. And that's why the range is just 0 to infinity, right? When the graph is shifted up or down, that horizontal asymptote would move, right? So if we added 2, like we're going to in the next example, this whole graph is going to shift up 2. So that horizontal asymptote, the line we don't cross, is also going to shift up 2. So let's take a look at this 3 to the x plus 2 and think about transformations. This plus 2 will shift the graph of y equals 3 to the x up 2 units, right? So we just graphed y equals 3 to the x, right? If we shift that up 2, our new points, we can still use x equals 1. Let's write down, we would have had 1, 3, 0, 1 on y equals 3 to the x. The points we have would look like this. So when we shift them, and I move everything up 2, the x doesn't change, but the y becomes 5. The x doesn't change, but the y would become 3. And the x doesn't change, but the y would become 2 1/3. Right? And because of this up 2 shift, that horizontal asymptote that used to be on the x-axis is going to be at the line y equals 2. So we're not going to cross that line, which means the range is going to be 2 to infinity instead of 0 to infinity, right? So we have 1, 5, 0, 3, negative 1, 2 1/3. So we can see the graph is going to go up as we go to the right and not cross 2 as we go to the left. The domain is still all reals. All right. Now the next one, instead of 3 to the x, we have 3 to the x minus 1. So what you can remember is, in terms of transformations, when there was a change with the x, that's a shift horizontally, so left or right, and it's always opposite of what it looks like. So a minus, we would think left, but it's going to actually go right 1. And then the plus 2, just like it did last time, would go up 2 from the graph of y equals 3 to the x. So the 3 has nothing to do with the shifting. That has to do with how we're going to choose our starting points. So the points, again, on y equals 3 to the x, we would have 1, 3, 0, 1, and negative 1, 1/3. So we use the base with the exponent x to get our starting points. and then we shift right 1 and up 2, the right 1 is going to change the x, and the up 2 is going to change the y. So you would have 2, 5, and this 0, 1 would go to 1, 3, up 2, and right 1, that would go to 0, and then up 2, 2 and a third. So again, now the horizontal asymptote is only going to move from the up and down shifts. Moving things left and right won't move that. So we'll have a horizontal asymptote again at 2, just like we did in the last one. And then let's plot our points. 2, 5, 1, 3, and 0, 2 and a third. So the same points as we had in the other graph, just shifted 1 to the right. The domain is all reals because it extends to the left and right, and the range is everything bigger than 2, just like it was in the last time. Alright, so now we're going to look at the inverse of an exponential function, and the name for that is a logarithmic function. And we've talked about this in the other sections when we were solving exponential and logarithmic equations. So to figure out what the graph should look like, what we want to remember is how a function and its inverse are related. So we're going to start with the graph of f of x equals 2 to the x, or y equals 2 to the x, and I'm going to put that in blue. And remember, for this graph, these are the ones we've just been doing. We'd have 1, 2, 0, 1, and negative 1, a half for our key points. So the key points, 1, 2, 0, 1, negative 1, a half. So the graph of y equals 2 to the x should have this shape. All right. And now if we want to think about the inverse, officially we would have x equals 2 to the y, right? X's and y's inverse of f of x equals 2 to the x would be x equals 2 to the y, right? And the points, we just switch the x's and y's, right? So we'd have 2, 1, 1, 0, and 1 half, negative 1. Alright, so if we plot the points on the inverse function, we would have 2, 1, 1, 0, and 1 half, negative 1. So my graph of the inverse is in black. So notice, just like we had when we looked at inverses in general, the x's and y's are switched, and the graphs are symmetric across the line y equals x. So if the graph of the original didn't cross the x-axis, this graph shouldn't cross the y-axis, right? We could think of some other points. When y is 2, x is going to be 4. When y is 8, when y is 3, x is going to be 8. 2, 4, 6, 8. But for this, what we want to think about is select y, then get x, which is what's opposite of what we're used to, right? We're used to saying what's x, then we'll find y. What's x, we'll use it to find y. Because y is in the exponent, we want to pick y first and use it to find x, and then we can make our list of points. So points that should be on the graph of the inverse, I listed those over here, but they would be 2, 1, 1, 0, and 1 half, negative 1, among others, but those are the ones we would focus on. So notice now, it's the y's that we're choosing to be 1, 0, and negative 1, because those are the exponents, right? So it's just like before, we take the exponent to be negative 1 and 0 and 1, but in the previous graph, the x was the exponent, and now in the inverse, the y is the exponent. The domain of the inverse is always the range of the original, so the domain should be 0 to infinity, just like it looks like from the graph. The range should be the domain of the original, and the domain of the original was all reals. The range of this inverse will be all reals. It extends down and up, right? So we already sketched the graph of the inverse, but if we try to solve for it algebraically, we get stuck. All right, we have x equals 2 to the y. We want to solve for y, and the only way we can do that is to use logarithms, right? So we would have the log base 2 of x is y, right? So the inverse function is the log base 2 of x, right? So the logarithmic function with base 2 is the inverse of the exponential function with base 2, right? So just like we talked about in the previous sections when we introduced the logarithm, what we need to do to find the inverse is to use that logarithmic function, right? So let's sketch the graphs of these logarithmic functions. So what I want to do is, if my function is y equals log base 2 of x, I think it's easier to rewrite the same expression. This is the same as 2 to the y equals x. Right? Those are the same thing. They're not inverses. Those are the same thing. Right? It's just the same relationship expressed exponentially instead of logarithmically. And then I'm going to pick my exponents, which are the y values, to be 1 and 0 and -1. And then I would use those to find the x's. So if y is 1, I'd have 2 to the 1 equals 2. 2 to the 0 equals 1. 2 to the -1 would be half. And we've got it. So my graph is going to look like 2, 1, 1, 0, -1. Sorry, 1 half -1. And it's not going to cross the y-axis. And we got it just like that, right? So we could also list the domain would be 0 to infinity, and the range would be all reals. And the x-intercept is 1, 0, and there's not a y-intercept. Right? So the next one, y equals log base 1/2 of x. I'm trying to graph. I would do the same thing. That's the same as, and switch it to exponential form. 1/2 is my base to the y equals x. And I'm going to, again, focus on these y values first. So I would take, for my points, y equals 1, and then y equals 0, and then y equals -1. 1/2 to the 1 would give me my x, which is 1/2. 1/2 to the 0 would give me x equals 1. 1/2 to the -1 would be the reciprocal of 1/2, which would be 2. So now I have 1/2, 1, 1, 0, and 2, -1. Once again, the graph is not going to cross the y-axis, but this time as it goes to the right, it's going to get smaller and smaller. Right? So if I wrote down the domain, it would just be 0 to infinity. The range is still -infinity to infinity, it's just shaped the other direction. It's decreasing instead of increasing. The x-intercept is 1, 0, and the y-intercept doesn't exist. There's not a y-intercept. All right, a couple more. Hopefully you got the idea. If f of x equals log base 6 of x, that's the same as y equals log base 6 of x. And then I would switch to exponential form. That's the same as 6 to the y equals x. And focus on the exponent, which in this case is the y. Then we use 1, 0, -1. You can pick others to use also, but make sure you get these three on there. So we'd have 6, 1, and a 6th for the x's. And then my graph, I'd have 6, 1. I guess that's already off my graph. 1, 0, and 1/6, -1. And just, mark that as close as you can. It's hard to get very accurate with these fractions, but we've got the right general shape at least. Should look like that. And let's list the rest of the details for good measure. Domain, we don't get left of the y-axis, so 0 to infinity, we don't touch the y-axis. The range, all reals. The x-intercept, 1, 0, and the y-intercept is none. Then f of x equals log base 1/5 of x would be the same as y equals, log base 1/5 of x, which I would express exponentially. This is not the inverse, it's the same thing expressed the other way. 1/5 to the y equals x. And again, focus on the exponent, which is the y. So put all these 1s and 0s and -1s in the y column. So we'd have 1, 0, -1 as our chosen exponents. 1/5 to the 1 is a 5th. 1/5 to the 0 is 1. 1/5 to the -1 is the reciprocal of a 5th, which would be 5. So 1/5, 1, 1, 0, and 5, -1. And we can see the graph is going to head up as it gets closer to the y-axis, and then it'll decrease as we go to the right. All right, and then domain, 0 to infinity, range, all reals, x-intercept, 1, 0, and y-intercept, none. So we talked about, on the exponential function graphs, we talked about a horizontal asymptote. We could talk about a vertical asymptote on these. There's a line that doesn't get crossed. That's a vertical line that's on the y-axis, right? And if we did any left or right shifting, then that would move and the domain would change. We're not going to do that in this course. That's something you'll look at in the next course, but you could at least see how that would happen. All right, and then the last question here is we've looked at bases that are nice, quote-unquote nice bases, whole number or reciprocal of whole number bases. We should also think about the graph of the natural log of x, since that's a common base that's used. So this would be the same as y equals log base e of x, right? And if we wanted to express that same relationship in exponential form, we'd have e to the y equals x, right? And so we would take our exponents, the y values, to be 1 and 0 and -1. E to the 1 would be e. E to the 0 would be 1. And e to the -1 we would just write 1 over e. So roughly we would think, remember e was like 2.71 or 2.718. So we'd have 2.718, roughly 1, 1, 0, and then 1 over 2.718, so like between a half and a third. All right. Then lastly here, I just have a summary of what exponential functions should look like, what key points to keep track of. and also what logarithmic functions look like, and the key points to keep track of. So you can look over that, but it's nothing that we didn't already discuss.